This time, I'm going to talk about PCA and Monte Carlo simulation for Vasiceck model in Python. In this video, I will use swap rates, treasury rates, and the spread between swap rates and the treasury rates as my input data. And I will perform principal component analysis. I will reconstruct data set from principal components, and I will calibrate Vasiceck model with 10-year spread. Finally, I will run Monte Carlo simulation for Vasiceck model. When I use the swap rates data, I have all those swap rates with 8 different tenors. We can consider each tenor as one dimension. So when I have 8 different tenors, we have 8-dimensional data. When we check this swap rates daily change, you can see returns are highly correlated across the maturities and fairly stationary. Since the correlation between yields is so high, we may run into the problem of multicollinearity. Then we can use PCA to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. This transformation is defined in such a way that the first loading points in the direction where data has the largest variance. Also, please note, one of the key features of PCA is the ability to reconstruct the initial data set using the outputs of PCA. This is how we can run this principal component analysis. First, we will detrain the data set by removing the mean of each column from our observations. Then we calculate the covariance and correlation matrix. Then we calculate the eigenvector and eigenvalues. Lastly, we will sort eigenvectors and eigenvalues based on decreasing eigenvalues. In this way, we can pick up the most important principal component from this principal component analysis. I have another video talking about principal component analysis in detail in my YouTube channel. If you haven't watched that video, you are welcome to watch that video as well. This is our result of top 3 principal components. As I mentioned before, for the swap rates, I have 8 different tenors. This is the shortest one, this is longest one. And when we check first principal components, this one, you can see this stands for parallel shift in yield curve. So it's the shifts across the entire yield curve. And if you check the second principal component, this one, and it is the changes in short, long rates. So it is either steepening or flattening of the curve. If you check the third principal component, this one, this is the changes in curvature of the model. So it is the twists. And then when we check the contribution of principal components, you can see the first principal component explains 95.249% of the entire changes. And the second principal component explains about 4.397% of the changes. And the third one explains 0.312% of the changes. So we see that the first three principal components account for almost all of the variance in the model, and thus we should just be able to use these three components to reconstruct our initial data set and retain most of the characteristics of it. You see, this is original data set, and after we reconstructed the data set, it shows like this. Visually, we can't tell the difference between those two. Like I mentioned in my previous slide, the first top three principal components represents almost all the characteristics of the yield curve. Now let's take a look at Vasiceck model. The Vasiceck model assumes that the short-term interest rate follows a mean-reverting process, where the rate tends to move back to a long-term average level over time. This is the formula of Vasiceck model. dr is a change in interest rate, and kappa is the speed at which the yield spread rates revert to the mean theta. So theta is long-term level of the mean. And of course t is time period. And sigma is the volatility of the standard deviation of the current interest rate at time t. It will create randomness. Here, noise term is normally distributed. And RT is short rate at time t. This item, kappa times theta minus RT, is expected change in the interest rate at time t. So this is the drift factor. And dt is change in time. And W is random market risk. It is represented by a Wiener process. So the first item, is known as drift component, and the second item is known as volatility components. In this video, I will use 10-year spread to calibrate Vasiceck model to determine kappa, theta, and sigma. And then I will run Monte Carlo simulation for Vasiceck model. Now, let's go to Python to see how I implement those. This is my implementation of the model in Python. I will upload this program to my GitHub, and you can download it and try it by yourself later. First, I need to download the swap rate data and the Treasury rate data from NASDAQ. You can go to NASDAQ to get your own data API key, and then you can download the financial data with your own API key. First, we'll get the data, and then we'll check how it looks like for this original data set. And then I will do this principal component analysis and check the contributions, and then I will reconstruct the data set from principal components. And after that, I will do the same thing for the Treasury rates, and also I will do for the spread between swap rate and Treasury rates. And after that, I will use 10-year spread to calibrate my Vasiceck model. And lastly, I will run Monte Carlo simulation for Vasiceck model. Okay, let's check our output. This is the data I got for the swap rates. You can see we have 1, 2, 3, 4, 5, 6, 7, 8 dimensional data here. And if you draw a graph, the rates change like this. And also, you can check the correlation between different tenors of the swap rates. Obviously, the swap rate will have very high correlation, it's 100% with itself, and then it decreases when the tenor becomes longer and longer. And then we can check the daily absolute return for those swap rates. And as I mentioned before, we can notice they are highly correlated among those different tenors. And then we will do this principal component analysis. This result I showed you with my slide. So basically, the top 3 principal components account for most of the changes. The first principal component accounts for the parallel shift of the yield curve, and the second principal component accounts for steepening or flattening, and the third principal component accounts for the twists of the yield curve. Of course, we can also check the impact of the fourth, fifth, and sixth principal components. Principal component 4 has impact like this, and the fifth one has impact like this, and the sixth one has impact like this. Of course, all those impacts are ignorable. And then I reconstructed the data set with the mean subtracted. It looks like this. After I add back the mean to the reconstructed data set, it looks like this. If you check my program, this is reconstructed mean subtracted data set, and here I just put the mean back to the reconstructed data set. And this graph shows very similar pattern with the original data set. When we check the contribution to variance, you can imagine the first principal component has most of the contribution, and the second one has much less, and the third one has even more less. And if we draw a graph for the Treasury rates, it shows something like this. And we can also check the correlation between different Treasury rates. And also we can check the variance explained by the principal components. You can imagine the first principal components has most of the contribution. And similarly, we can also check the top 3 principal components of the Treasury rates. This is very similar to the swap rate. And you can check the spread between swap and Treasury, and shows the spread look like this. And then I used the 10-year spread to calibrate the Vasiceck model. You can see for the Vasiceck calibration, I use 10-year spread rate. And after the calibration, we got the parameters. Kappa is 4.222, theta is 0.003, sigma is 0.009, and R0 is minus 0.002. And of course, with those calibrate parameters, we can run the simulation. This is one pass of the simulation. If we run the simulation for 100 times with calibrated parameter, the result will show like this. Remember, kappa means the speed at which the yield spread rates revert to the mean theta, and the sigma means the volatility or the standard deviation of the current interest rate at time t. Let's check out if we change kappa or sigma, what kind of impact will cause to our Monte Carlo simulation. If we scale up kappa by 5 times, remember kappa means the speed when the interest rate revert to the long-term mean. So the graph will look like this, comparing with the original graph. So the interest rates tend to revert to the long-term mean much faster than the original simulation with calibrated parameters. And if we scale up sigma by 5 times, and you can see the Monte Carlo simulation shows a graph like this. Please note the scale of this graph is from minus 0.01 to positive 0.01, but this graph is from negative 0.05 to positive 0.05. So that means the volatility of this Monte Carlo simulation is much larger than this one. This is how you can perform principal component analysis to your interest rate model, and how you can run Monte Carlo simulation for Vasiceck model in Python. Please provide your comments and subscribe to my YouTube channel. Thank you for watching.